Welcome to lecture 20 of Machine Learning from Data. We're going to begin discussing neural networks, a very popular learning model these days. Okay? And we will begin that whole discussion by first deriving the multilayer perceptron. Now, before we get going, let's have a quick recap. We started with the foundations and the linear models, and then we moved to similarity-based methods. Perhaps the simplest of all methods, perhaps the method that the 5-year-old uses. Okay? And in sort of discussing these similarity-based methods, we talked about the k-nearest neighbor algorithm and the radial basis function networks. Okay, so these are very powerful methods. Okay? And in discussing these methods, we found a use for unsupervised learning. Okay? In the k-nearest neighbor algorithm, you have to find the nearest neighbor, and if you store your data in convenient geometric structures, then the efficiency of that search for the nearest neighbor can be significantly enhanced. Okay? And in the radial basis function network, we have to decide the centers of the bumps. And one good way to decide the centers of the bumps is to represent the data, i.e. to organize the data into clusters and pick as a bump center the centers of those clusters. Okay, so that's what we discussed in the last lecture. We discussed methods, a very, very short sneak preview peek at unsupervised learning. And let me emphasize, it was in some sense unfair. Unsupervised learning is a huge, huge area. And we just gave it one lecture because we have to move on. But in that one lecture, we discussed k-means clustering, a very powerful technique for clustering, and we discussed Lloyd's algorithm. Okay? And then we sort of, moved to probability density estimation, a sort of soft generalization of clustering, and introduced you to the Gaussian mixture model, another very powerful technique for sort of modeling and representing and structuring the data. Okay? Now, unsupervised learning is important on its own, because you can get a lot of information out of a good organization of the data, but it's also important for supervised learning. Okay? So those are sort of the messages from the last few lectures. Now, let's start talking about neural networks. And neural networks are, in some sense, a biologically inspired learning model. And what better than biology to inspire us in computer science? Because biology seems to have gotten lots of things right. Okay? So let's start, with sort of, a brief sort of perspective on the history of neural networks. And yes, I show you a cartoon of a neural network of a brain, and think of this as the biological inspiration for neural networks. Okay, and indeed, that's sort of how the whole field started. Okay, starting about 1943 with the McCulloch and Pitt neural network. Okay, but really, neural networks started perhaps in 1958, with the Rosenblatt perceptron. Okay, and neural networks were dealt a blow in 1969 when Minsky and Papert sort of revealed this Xor and the inability to sort of fit simple functions like the Xor, and also the inability to sort of easily generalize the Rosenblatt perceptron in a way that's easy to fit to data. Okay? And so, this blow basically meant that neural networks subsided and they sort of disappeared because we couldn't do much with them, even though they had biological inspiration. Okay? Around about the late 80s and late 80s, the neural networks in some sense were revived. Okay? And what changed? What's changed was sort of the arrival of the multilayer perceptron in around 1986. The multilayer perceptron was sort of this generalization of the Rosenblatt perceptron, and we'll discuss the multilayer perceptron today, and its generalization that led to an ability to fit the data well. Okay? This what's called, the back propagation algorithm. Okay? Around 1986, and neural networks at that point took off again, okay? Because now we had a way to sort of fit more complex functions similar to the Xor, and we had a way to do it efficiently using gradient descent, which is a technique we've already seen before in the context of logistic regression. Okay, so neural networks took off, and around the early 90s is for example, when I got interested in neural networks. Okay, and then again in 1992 to 1995, neural networks were dealt a blow. Bam! Okay, now it wasn't so much an algorithmic blow. It was more of a statistical learning blow, something related to the foundations that we have discussed. Okay, so as we will see with different techniques, some techniques come in, some techniques go out, but at the end of the day, you cannot avoid the foundations. The foundations are going to hit every technique equally. Okay? And how were they hitting the neural networks? Well, the neural networks were this sophisticated learning model that could easily overfit the data. So the promise of the neural networks was not being realized. They were overfitting like hell. Okay? And people were getting burned. And so neural networks gradually lost out and eventually got completely wiped out in terms of popularity of use by the arrival of this very powerful and very robust technique called support vector machines in the mid-90s. Okay? And we will talk about support vector machines later. Okay, so it's very robust, and also, very powerful, so able to model all kinds of things, including the things that stopped the neural networks in the 1960s, this Xor and the inability to do complex target functions, which sort of halted the neural networks in the 1960s, was overcome easily with the support vector machine by combining this robust linear model. So it avoided the pitfalls of overfitting with the nonlinear transform, which we have seen before. So all the foundations that we have seen before came in the mid-90s and hammered the neural networks. Okay? But then the neural networks started resurfacing again around 2005, 2006, with the arrival of sort of deep belief networks and the ability to sort of these new training algorithms for large deep neural networks that went layer by layer, and the concept of pre-training the neural network. And then they showed up with a real splash in 2012. Okay, when deep networks were used, to sort of classify, images. And so I'm showing this in the picture here from the Hinton paper in 2012. Okay, and Hinton recently won the Turing Award, basically he shared it basically for the developments of deep networks, and especially towards sort of vision. Okay, so here you see some test images, and the deep network has basically got it right. Okay, so for example, this red car is human classified as a grill because that seems to be the focus of the picture. But the algorithm says the most likely classification is a convertible, then a grill, then a pickup, then a beach wagon, then a fire engine, and you can see the rationale for each of those classifications. Okay, so there was this great success of deep networks for vision. Okay, and that that sort of inspired a huge surge in the popularity of neural networks. That we can now learn again with neural networks in a robust way. Okay, which was the flaw before, and what led to the support vector machine killing the neural network. We can now learn, okay, and what changed? Okay, so. In the 1960s, it was the deficiency of the neural network that killed it. Okay? And what changed was the arrival of a new algorithm that allowed us to train, more complex neural networks on data, and so then it resurged. But the problem was overfitting, was inability to generalize to out of sample, and that's what killed it in the mid-90s with the arrival of the support vector machine, which solved that problem. Okay, so why is it coming back? So now we are able to sort of deploy the complexity of the deep networks, okay? Because of A, we can efficiently train them, okay? And B, okay? This concept of pre-training allowed us to use networks, huge networks trained on large data sets, okay? And then fine-tune them on the data set of interest. But most importantly, we now have lots and lots of data. That is the primary reason why we can get more robust to noise. Okay, we have lots and lots of data. So we train deep networks in huge databases, and then we can sort of transfer that learning to the domain of interest. Okay? And so neural networks are back. But who knows? The lesson here is that certain models may come in and go out, come in and go out. And at one time, the in thing was the support vector machine. And now the in thing is the deep network. But, if you are well versed with the foundations, you can understand why certain things come in and go out. And, okay, you can adapt to the changing landscape. And you know how to control these various models. Okay. So, that's a brief history of neural networks. Today they're very popular and for a good reason. As you can see from this picture, they're doing a reasonably good job at a task that humans do well, and they seem to be doing it almost as well. So neural networks have now become quite sophisticated for vision, and they've infiltrated into all kinds of other areas: speech, natural language processing, all over the place. Okay. But it's very important not to use them blindly. So that's what the sort of next set of lectures is all about. We're going to get into the nuts and bolts of neural networks. Okay? And as you will see, you cannot avoid the foundations. So you have to deal with the E-in issue and the E-in versus E-out issue. Okay? And it is the fact that these two have been to some extent dealt with that allows neural networks to be deployed at the scale that they're deployed today. But if you're going to deploy neural networks, you need to know how to control those two steps of learning with this very powerful, machine learning model. Now, when we discussed the linear model, we said that you've got the linear model, it's a sports car. Now you add on to the linear model the nonlinear feature transform, and it becomes an 18-wheeler. Very hard to stop, very hard to control. It just eats up the data and overfits. Okay? And so the neural network is, an 18-wheeler squared. Okay? So you really need to know how to handle these neural networks. Now it is true that you can download packages, and they dealt with things like regularization, and they implemented various basic things for you. Okay? But you still can't take even a downloadable neural network package and apply it to a 1,000 data point data set. Okay? You'll just overfit like crazy. You need to know how to choose the architecture of the neural network. And you need to know why it will work and when it will work. Now, to some extent, we haven't fully understood those issues. But one of the things we do understand is that they work best when they have been pre-trained on huge data sets outside, okay, in order to sort of extract reasonable, representations of features at different levels, and then the final level features are ultimately what are combined as a linear model. Okay, so in a nutshell, neural networks are combining linear models in a cascade fashion, okay, and that cascade fashion of combining linear models gives a huge amount of power, and that's what we're going to discuss today. And in discussing the cascading of linear models, we're going to derive the multilayer perceptron. Okay, before we get going, let me just sort of take with a grain of salt this notion of the biological inspiration of neural networks. In the early days, yes, the neural networks were biologically inspired. But today, the neural networks are built in a different way. They are built for engineering success. They're built to get E out small. And so they don't look really anything like the biological counterparts. And that's okay, because what we care about is engineering success at the end of the day. Although, it's nice when you can sort of get inspiration for biology. And now here's an analogy, birds fly by flapping wings. And that's what inspired us to fly. First, that it's possible. And second, gave us some hints as to how to do it. But we tried in the early days to flap wings. It didn't work. Engineering success has resulted in the plane with jet engines and so on and so forth. So we don't flap wings to fly. And that's driven not because we don't want to be biologically inspired, but because at the end of the day, what matters is the engineering success. Okay? And so we'll bear that in mind when we're building our neural networks. Now, let's start talking about the multilayer perceptron. In particular, let's start with the Xor problem of Minsky and Papert that led to the initial downfall of the neural networks. Okay? So basically, they revealed that the linear model, the perceptron, has a real limitation. This Xor function, which you think of two lines crossing, and opposite regions are the same classification. So opposite blue regions and opposite red regions. Okay? And if this is your target function, it's relatively simple, but there's no perceptron that can come anywhere close to this. And you can come up with other simple target functions that the linear model cannot do. Now, we try to address this with nonlinear transforms, but you'd need a very contorted nonlinear transform in order to implement this. Okay. And, what we're going to discuss is another very simple approach, okay, that will not only allow us to do this Xor function, but it'll open the floodgates. We will essentially be able to do anything. And what's that simple approach? The simple approach is, instead of, is to cascade the linear model. So it's still the linear model, but we're going to cascade. Now, let's first start by showing how cascading of linear model can allow us to do something like this complicated Xor function. Okay? And that'll lead us to the general multilayer perceptron. Okay? And we will then build sort of the general notation for neural networks and show how we get in a very simple way from the multilayer perceptron to the neural network. Okay? So the main goal today is to sort of demonstrate the power of cascading linear models. Okay, and then take that power to build the multilayer perceptron, okay, and introduce the notation for the multilayer perceptron and ultimately for the neural network, okay, as a very simple extension of the multilayer perceptron. Essentially, the neural network will be the multilayer perceptron, but made more convenient so that we can run algorithms, okay, in particular gradient descent. Okay, let's get going. Let's go to the board. We're going to derive the multilayer perceptron, and what I'm showing here above here is this problematic Xor target function, okay, where you have two lines crossing, opposite regions are the same classification, opposite minus, opposite plus. Okay. Now, it's interesting to observe that this complicated target function can be decomposed in some sense into two pieces where one of the pieces is this line, so that's a linear perceptron, and we can definitely implement that guy as the sign of W1 transpose X. So let's call this perceptron H1 of X. Okay? And the other part of this
complicated XOR function is again, a linear perceptron, this guy here. And that again, we can definitely implement with a perceptron, H2 of X, which is the sign of W2 transpose X. Okay. So, and I'll explain shortly why, this decomposition helps us a lot. But before we get there, I want to show you a nice, convenient visual way of, looking at perceptrons, okay, of representing perceptrons. And that'll be very helpful for sort of following what we're about to do with neural networks. It turns out that, the sort of easiest and most pleasing way for us to talk about neural networks is using a graphical visual representation of neural networks. So let's start with a graphical visual representation of the perceptron. Okay. So here we're taking sign of W1 transpose X, okay, where X is X1, X2. Okay. Now, this visual way of representing this perceptron is to say, well, we have, an initial weight, W0 here, okay, and then the weight that multiplies X1 and the weight that multiplies X2. Okay. So the way I'll represent that is, I'll put in a 1, this is our augmented 1, okay. Here we have X1, and here we have X2. Okay, so think of that as the input. Okay, now each of these gets multiplied by the corresponding weights. Okay, so they get multiplied by, W1, if I wanted to call it 1, 0, W1, 1, and W1, 2. Okay, so, okay, and then you take this input, multiply by its weight, take this input, multiply by its weight, take this input, multiply by its weight, and sort of feed that in to the sign function, okay? And out pops the sign of, W1 transpose X. Okay? So this is a nice visual graphical view of what's going on in a perceptron. Think of it as, you take inputs, you pass them along edges. These edges have weights. The weights multiply what's being passed along the edges, multiply, you add them up at this node, you pass it through the sign and spit out the final result. Okay, and we can represent this guy as well. So you have, 1, X1, X2, okay, and same thing, okay. Send it into the sign function, okay. And you output the sign of W2 transpose X. And so on here are the weights W2. Okay, so this is a nice visual representation. Now, you might wonder, well, why did I decompose this complex function into simpler things? Because as usual, when you try to solve a complicated problem, first, analyze its simpler parts. Okay, and now specifically, mathematically, why this decomposition is useful is because, look, if we call this the target function, okay, f of x, okay, then f of x is equal to, so in this region, h1 is plus 1 and h2 is minus 1. Okay? So you could think of that as h1 is plus 1 and not h2 is plus 1. So this is h1 and not of h2. Okay? And in this region, h2 is plus 1, okay? And h1 is minus 1 in this region. And we will say, so either, for f of x to be plus 1, either h1 is plus 1 and h2 is minus 1, or, okay, h1 is minus 1 and h2 is plus 1. So think of this as the AND of h1 and h2 bar. Okay. And think of this as the AND of h1 bar and h2. And here I have an OR. Now, this is sort of somewhat standard notation in computer science and electrical engineering, where we represent AND by multiplication and OR by addition. Okay, and I will formally define these things right now. Okay, but for the moment, we can see that using the and the OR operator, okay, we can decompose this complicated target function into and ORs of these two simple functions. And the reason we're doing this, okay, is because these simple functions are perceptrons. Okay. Now, let me formally define and OR. Okay, so and of, let's say, and I'll give you the full definition, the AND of, any number of inputs, x1, x2, up to xd. Okay, the AND of any number of inputs is equal to, plus 1 if all the inputs are plus 1, x1 equals x2 equals xd equals plus 1, and minus 1 otherwise. Okay, so it's a standard AND function. Think of plus 1 as positive, okay, and minus 1 as 0, or plus 1 as true, or minus 1 as false. So the AND is true, the AND is plus 1 if all its inputs are true, if all its inputs are plus 1, and otherwise it's false. Okay? And the OR of x1, x2, and so on, xd, okay, is very similar. Okay? The difference being that the OR is true if one of its inputs are true, and it's false only when all its inputs are false. So it's minus 1 if x1 equals x2 equals ... equals xd equals minus 1, and it's plus 1 otherwise. So there, I formally defined for you the AND and the OR. Okay. Now, let's consider, so where are we going here? So why am I introducing you to all kinds of weird stuff? Okay, I'm introducing you to Boolean functions, okay, and we decomposed f into linear perceptrons, okay, which have this nice visual representation, very nice. Okay. And okay, there seems to be a reason to do this because the target function can be reconstructed using these simple hypotheses, these simple functions, and Boolean operators. Okay, so that much we have, but so what? Who cares? Okay, and here's the punchline. So punchline. Okay. And OR, these guys are linear perceptrons. And OR are linear perceptrons. Okay. Bam. And so now the fog should slowly be clearing. Okay. So if H1 and H2 are linear perceptrons, and the ANDs and ORs are linear perceptrons, okay, then F is somehow a complicated combination of all kinds of linear perceptrons. So let's prove this. Okay. So pop quiz / exercise. Okay. So in this visual representation, let us consider, the AND of two inputs, and it generalizes easily. So the AND of two inputs. So 1, x1, x2. Okay, so the AND of two inputs. Okay, and we're going to pass this through a sign. Okay, and what's going to come out of here is the AND of x1, x2. Okay, and the OR is going to have a similar visual representation. Okay, so 1, x1, x2. We're going to pass it through weights, multiply, and then send it into this sign function. And out should pop the OR of x1 and x2. Okay. So exercise and do it. Pause the video and just do it. Okay. What should we place on as edge weights? Okay, just like we discussed here. Okay. So what should we place as edge weights? Okay, in order to implement the AND as a linear perceptron, and in order to implement the OR as a linear perceptron. Okay, so work it out. I'll give you a few seconds. 1, 2, 3, 4, 5. Okay, so if you worked it out, great. If you're here just for the ride, okay, please pay attention because this is important. Okay. The specific weights are not so important, but the fact that we can represent AND and OR as linear perceptrons is important. Okay, so how are we going to do it? So let's think about this. Okay. So AND has to be plus 1 only in the situation where all of these are plus 1. Okay? So here's what I'm going to do. I'm going to add a weight of plus 1 here, plus 1 here, okay, and minus 1.5. Now let's see, does that work? Okay, if one of these is minus 1, okay, then these two sum to 0, and you get a minus 1.5 coming into here, and you get minus 1. If both of these are -1, it's even worse. The only way that the thing coming into this sine function is positive is if both of these are +1, in which case they counteract this -1.5, feeding in 0.5 here. And now you feed in 0.5 here, boom, out comes +1. So this perceptron implements the AND. Okay, so now hopefully if you didn't do the OR, you are now ready to do the OR. I'll give you another couple of seconds. Okay, here, 1, 2. Okay, so let's do the OR. And the OR is the opposite. Okay, if both of them are -1, that's the only situation where you will output -1. Okay, so what I'm going to do is I'm going to add a weight of +1.5. You can think of this as a bias of 1.5. Okay, and now I can add weights of +1 and +1 here. Okay, and what we will see is that, okay, the only way in which you can get a negative input into this sign is if both of these are -1. Then you get -2 plus 1.5 gives you -0.5, and the OR produces -1. In all other situations, you know, this plus 1.5 can counteract what's going on here, so that what's feeding into this sign is +1. So, you know, if we wanted a mathematical prescription and of x1 and x2, and of x1 and x2 is exactly the sign of -1.5 plus x1 plus x2. And OR of x1 and x2 is equal to the sign of 1.5 plus x1 plus x2. Okay. Now you should easily be able to convince yourself that, you know, we can represent the general AND and OR of D inputs using a perceptron. Okay. So at least we see that AND and OR are perceptrons. Okay. So, you know, having proved that, okay, I'm going to erase this. Okay. So all we really need is the facts that AND and OR are perceptrons. And now I'm going to show you how to implement f of x, okay, only using perceptrons. So let's erase. Now I'm going to show you that f can be implemented using only perceptrons. F of x, the target function f of x, can be implemented using only perceptrons. And here's the basic idea. So the first observation is that f is the OR of two things. If I had those two things as inputs to a perceptron, okay, then I can create the perceptron to implement the OR of those two things. What are those two things? H1, H2 bar, okay, and H1 bar, H2. So let's just imagine that I have those as inputs to my perceptron. Okay. So I have as inputs to a perceptron, okay, H1, H2 bar, and H1 bar, H2. Okay. And let's augment with a 1. So we always, you know, have this augmented 1. Okay. And I want to take the OR of these two inputs, and we know how to do that with a perceptron. We just discussed that. Okay. So I'm going to have weights feeding in to the sine function, and the output is going to be f of x. Fantastic. And we know how to set these weights. These weights are plus 1.5, 1, and 1. Okay. And now I'm implementing the OR of these two inputs, which I don't know how to get them yet, but I'm just assuming that if I had those, okay, then I could implement the OR using a perceptron. Okay, fantastic. Okay, but what is H1, H2 bar? It's the AND of H1 and H2 bar. Okay, and what is H1 bar, H2? It's the AND of H1 bar and H2. And we know how to implement AND with the perceptron. Okay, so what I want to do, okay, so and what would be the inputs? Okay, so it looks like the inputs are H1 and H2. Okay. Well, technically H1 and H2 bar, but it's easy to convert H2 to H2 bar, because H2 bar, the negation of H2 is just negation. Okay, so plus 1 becomes -1, -1 becomes +1. Okay, so if I have inputs H1 and H2, I can easily compute the negation of H2. Okay, and you know, and then I can easily compute the AND using a perceptron. Okay, so let's see how that would work. Okay. So here, if I have, you know, imagine that I somehow had constructed the inputs 1,
H1 and H2. Okay. Then the AND perceptron, okay, has, you know, minus 1.5 here, 1. Okay, let me do it in blue. Okay. It's going to be useful to do it in blue. So the AND perceptron has, you know, minus 1.5, 1, and 1. That would be taking the AND of H1 and H2. Send it through the sign, and what comes out is the AND. But I need the AND of H1 and H2. Bah! So what should I do? Think about it for a couple of seconds. 1, 2, 3. Okay, I gave you 3 seconds. Well, the AND of H1 and H2 bar, I have to first negate H2. Okay? But that just means multiply it by minus 1. Okay? So multiply by minus 1 and then multiply by 1. That's the same as just multiplying by minus 1. Change this sign to minus 1. Okay? And now send it in here. And instead of, you know, so, and if I indeed, you know, have these guys H1 and H2, and now I send it through the sign here, what will be coming out is exactly the AND of H1 and H2 bar. Let's use the same idea to compute the AND of H1 bar and H2. Okay, it's not going to be hard now because we've done it once. So and I'll use red. So here, I'm going to have weights, okay, edges, okay, and this is another AND, so it's going to be minus 1.5. Okay. Now, if I were computing the AND of H1 and H2, these weights would both be 1. But I need the negation of H1. So this weight becomes minus 1, and this weight becomes plus 1. Okay. If I wanted to be sort of, you know, meticulous, I would put plus 1 here. Okay. And here, I would put plus 1. Okay. So, if I had H1 and if I had H2 as inputs, I can implement two ANDs, which are just perceptrons. Okay. That gives me, so here, I need to now compute the sign. So that gives me H1 and H2 bar going out of here, and that gives me H1 bar and H2 going out of here, and I can implement the OR, and we're all set. Boom, I've got f of x. Okay, okay, good. But so what? We still need H1 and H2. But H1 and H2 are perceptrons. That was the whole reason why we decomposed this f of x into two lines, because we can implement those two lines as perceptrons. So I can indeed get H1 and H2. Okay? From what? From my inputs, x1 and x2. Okay? So here is how. 1, x1, x2. Okay. H1 is a perceptron given by the weights W1. So, you know, W1, you just heuristically put W1 for my weights here. Instead of it now and take the sign, what's coming out of that node is exactly H1. Because by construction, H1 is a perceptron. Similarly, okay, H2 is also a perceptron, but it has different weights. Okay. So H2 is also a perceptron. Okay. But it has different weights. Okay. And those weights are W2. Okay. And now I send it through the sign. And indeed, I have H2 coming out of here. Okay. Then coming out of here will be, by construction, will be H1 and H2 bar. And this will be H1 bar and H2 coming out of here. And then this takes the OR. So coming out of here will be H1 and H2 bar or H1 bar and H2. Exactly the function f. Boom. Okay. I have computed f using only linear perceptrons. Okay. So check. Check. Okay. But let's see what it entails. And this is the real punchline. So I started with my perceptrons H1 and H2. Great. Okay. And those became, you can think of it as the first layer perceptrons. Okay. I put on top of that, in other words, I cascaded this
with another set of perceptrons. You can think of that as my second layer perceptrons. Okay? And then I cascaded these two perceptrons with a third layer perceptron. Okay? So in order to implement this fancy target function, what did I need? I needed the ability to cascade layers of perceptrons. Okay? I needed the ability to cascade one layer of perceptrons into another. So I have multiple layers of perceptrons. What did I need? What did I need? The ability to use multiple layers of perceptrons. Multiple layers of perceptrons in sort of this cascade fashion. In a cascade fashion. Okay. And hence, so the original guys are called perceptrons. Okay. And this is called the multi-layer perceptron. The multi-layer perceptron, or MLP for short. Okay. MLP. Okay. And that gave me the power to implement this more complicated target function f. Okay, so I needed the ability to, cascade multiple layers of perceptrons, and also I needed the ability to be able to set the weights on these edges. Okay, so that's what we mean by using combinations of perceptrons. So each perceptron can have, in theory, its own set of weights. Okay, so I change the weights on each perceptron to accomplish goal, i.e., reproduce f of x. So I change the weights on each perceptron in order to reproduce goal. Now it turns out that the perceptrons in the final layer is just one perceptron, which is an OR. Okay. But the perceptrons in this layer, the second layer, are all different in the sense that they can be different ands. Okay, so you see the weights are different going into this node versus going into that node. Okay. And here they're clearly different because they depend on what these lines are. Okay. All right. I'll just make a couple of observations. Okay, a few observations. About multi-layer perceptron. One. Okay. Well, the last layer is an OR. Last layer is an OR. Okay. It's an OR of what? It's an OR, okay, that is taking an OR of sort of the representation of each plus region in my function. So here I have, in this plus region, it's H1 and H2 bar. Okay, H1 and H2 bar. So H1 is positive, H2 is negative. Here, H1 is negative, H2 is positive. So each of these plus regions, okay, are coming in as a separate input, and then I take an OR. So the last layer is an OR of the positive regions. Okay. So if I had had more positive regions, I would have just had a wider perceptron here because I need more than two positive regions. Fortuitously, I had just two positive regions here. But you could imagine that you can have more than two positive regions. You can even have fewer than two positive regions. Okay. The number of inputs in this second layer, okay, corresponds exactly to the number of hyperplanes, the number of linear perceptrons that I need in order to decompose F. So here I have H1 and H2. So that's my second observation. My second observation is the number of, let's say, the width, the number of inputs into the perceptrons in the second layer, number of inputs to perceptron in second layer equals
number of perceptrons used to decompose the target function f that I was interested in. Okay. So you have your inputs that are feeding in with the corresponding weights for each perceptron that is used to decompose f. So you have a set of weights for each of the perceptrons used to decompose f. Okay, and okay, so those weights are all different, and then you take these inputs that are used to decompose f and combine them into ands. Okay, and then you take one final OR. So the final multi-layer perceptron has, okay, so the input layer we typically don't count as a layer, has 1, 2, 3 layers. So the final perceptron has 3 layers. Okay, and so in here we have the number of nodes is equal to number of perceptrons in F, and in here we have that the number of nodes is equal to the number of positive regions in F. And you can see that what's going on here is an OR of the positive regions, where each positive region is an AND. So we're taking an OR of ANDs. That's very related to a sort of technique in computer science called DNF, disjunctive normal form, OR of ANDs. And basically, from sort of circuit theory or the theory of Boolean functions, we know that we can implement any Boolean function as an OR of ANDs. Where the Boolean function is a Boolean function of, let's say, D inputs. You can implement any Boolean function as an OR of AND. So that sort of hints that maybe we can implement any function. So let's move to the next sort of surprising conclusion, and this is a really surprising conclusion. Who cares about this function in practice? In practice, we have an arbitrary target function represented by a data set. Okay, we need to be able to fit that data set. Okay, even better, we need to be able to fit that target function. So can this cascading methodology work for more general target functions? Okay. So what we will do is we will prove by picture, you can see the text for more details, okay? But we will prove by picture that this 3-layer multi-layer perceptron architecture is sufficient for essentially fitting any target function, for essentially fitting any data set. That's the miracle of today. This 3-layer multi-layer perceptron, this multi-layer perceptron with 3 layers is sufficient to basically do anything. That's how powerful this strategy of cascading perceptrons is. And if you give me more layers, i.e. if you go to the deep network, you're giving me way more power. It turns out that I can even get away with just 1 extra layer. So this 1 extra layer, it turns out, is sufficient. But we will show that 3 layers is sufficient. It takes a little bit more work to show that 2 layers is sufficient. Okay? So you don't really need deep networks. You can do things with shallow networks if you give me as many nodes as I want in each layer. That's what we'll show next by picture. Okay? So it's an interesting challenge for you. So take your favorite application where you're using a deep network and see if this theorem really holds that we're about to demonstrate. That you don't need that deep a network. You can do it with a shallow network if it's wider. And how much wider you need? Well, we don't really understand too well the relationships between the width and the depth. Okay? But theoretically, you don't need depth. Sometimes we find that it might help in practice, but you don't need depth theoretically. Width is enough. Okay? So let me demonstrate that theorem without proving it rigorously, okay? And then we will move on. So let me erase. Erase all this. Universal approximation. And I'm going to use my favorite proof method, proof by picture. Okay, so universal approximation.
proof by picture. Now, of course, those of you who are analysis inclined can go and put the meat into this proof. It's not going to be hard to do. You've got to get your epsilons and deltas all in agreement, and you can pull it through. You need to know the analysis, though. You need to know something about convergence in convergence of functions and so on and so forth, and limits and etc. But the basic idea is that using an architecture like this, if you allow me any number of perceptrons, and if you allow me any number of positive regions, okay, and the ability to combine with and the ability to combine the final with or in the final layer, then I can basically do anything. Okay? And so here's the proof by picture. So let's try something that looks reasonably hard to do with linear perceptrons. Okay? So I'm going to have let's think of a circle. The idea is think of this circle as a generic boundary, a generic decision boundary that's smooth. Okay, so that's the idea. Now, how do I do this with perceptrons? Well, you can never do it exactly, so that's the idea of universal approximation. With a large enough, multilayer perceptron, large enough means enough nodes in the first hidden layer. These are called hidden layers, by the enough nodes in the first hidden layer and enough nodes in the second hidden layer. I can get arbitrarily close. So let me show you an approximation to this circular region, okay, that this circular boundary that can be approximated with 4 perceptrons. So let me first tell you what's the classification problem, what's the target function. So inside here is plus, okay, and outside we are minus. So outside we are minus. Okay, so we're minus outside. Okay, so here's my first attempt. Okay, so I'm going to put a line here. One of my perceptrons, let's call it W1, with positive inside. W2 with positive inside. W3 with positive inside. And W4 with positive inside. Okay? So what will that implement? That will implement, so if you think of these as H1, H2, so let me label these now H1, what was this? This was H1, this was H2, this was H3, and this is H4. Okay, so when they're all plus, so H1 and H2 and H3 and H4, think of the plus as the plus direction of each perceptron is pointing inside. Okay, so H1, H2, H3, H4 gives me a positive square region. Okay, and so this is just, in this case, it's just one positive region. So I'm just going to have one guy, and taking the OR of that is sort of trivial. Okay, you take the OR of that. The OR of one guy is just the guy itself. Okay, but that doesn't look like a very good approximation. Okay, so now let me add a few more. So because what's the error? The error that I'm making, I'm going to call this red region plus, this red region plus, plus, plus. Well, no problem. Give me a few more lines. So this is 4 lines. Now let me add some more dotted lines. Okay, boom. Okay, boom. Boom. And boom. Okay, so now again, everything inside. So now I'm classifying as +1 everything that's inside all 8 of those with 8 regions. So let me show you what's the region of error. The region of error now is this small green region in here, this small region here, this small region here, okay, and here, and this small region here, this small region here, this small region here, and there's a small region here. Okay, not drawing too well, but you get the idea. And you say, oh, I'm not happy with that. Okay, let's add another 8 perceptrons. So where am I going to add those 8? I'm going to add those 8 here. 1, 2, 3, 4, 5, 6, 7, 8. And there, you've pretty much got your circle now with 16 perceptrons. Okay, so 16 perceptrons. Okay. Now you can take this. You can basically take this proof by picture to the bank. Except that if you want to sit down and do the analysis and get the rigorous proof, you're welcome to do so. Okay, but what do I need here in this particular example? The 16 perceptrons corresponds to 16 nodes. So the width of this layer will be 16. And then we compute one AND. We compute the AND of all of those, and the OR layer is pretty trivial. Okay, it's just one positive region. Okay, if I have a very complicated target function with multiple positive regions, okay, if I have 3 positive regions like that, then I might need, I'll need 3 nodes in here, and I might need, 48 perceptrons. Okay, so I'll put 48 nodes in here. And you can see that if you give me arbitrary width here and arbitrary width here, I can basically do anything. That's the content of universal approximation. That's how powerful it is to cascade what? To cascade what? To cascade linear perceptrons. All we're doing is cascading linear perceptrons. Okay? And basically, what is the power that I need? I need the power to cascade linear perceptrons and then pick whatever weights I want on the edges. So what's the power I need? The power I need is 1. Cascade linear perceptrons. And all I need is 3 layers. So 3 cascades, 3 layers. Okay. Width of first layer corresponds to number of perceptrons in the decomposition of my function of interest, corresponds to number of perceptrons. And the second layer corresponds to ANDs for each positive region. Okay, and then the third layer is just one big OR. Okay. Now, in order to implement the first layer perceptrons, I need to be able to set the weights. So that's the other ability I need, the ability to set the weights on each perceptron. Now it turns out that, I really only need the ability to set the weights in the first layer, which defines these individual perceptrons, because the second layer is computing all ANDs, and the third layer is computing an OR, and so those weights can be fixed. If I wanted to do it that way, but, we can get more flexibility by giving us the ability to even change these weights and do more than just AND in this layer and do more than just OR in this layer. And imagine the power I get then. Superpower. Okay. Avengers. Okay. So, you can imagine that if you give me this so you can imagine you give me this ability to add as many perceptrons as I want, as many positive regions as I want, the ability to change all the weight, I have a huge amount of fitting power. Okay, so huge amount of fitting power, i.e. approximation capability. Now let's go back to the foundations, and I'm going to ask you, so what am I sacrificing for that? Think back to the foundations. Think back. Approximation versus what? Generalization. Okay. So yes, I've gained a huge amount of approximation capability, but generalization is going to be an issue. What about versus generalization? Question. Exclamation point. You can't escape the theory. And we'll discuss this, question a little bit later. But the bottom line is, the more nodes you give me in this layer, in other words, the more individual perceptrons you give me, okay, and the more nodes you give me in this layer, the more positive regions I'm allowed to use, okay, and then I can set all the weights at will, okay, you are significantly increasing my approximation capability. That's what my approximation capability depends on, which is, what we call the architecture of the multi-layer perceptron. Okay. And, imagine now if I go for more than 3 layers, if I go for the 4th and a 5th and a deep network, wow! Okay. Your approximation capability is going to skyrocket through the roof. So generalization, we have to really work hard to get that under control. Okay. You can never escape the foundations. You cannot. Don't try to. Every time you try to escape the foundations, you will fail. Okay. So we're going to have to deal with that. The second question we're going to have to deal with is, for these simple problems, I was able to sort of figure out, how to set the weights, given the weights of the multi-layer of these individual perceptrons. Okay? But in general, now I'm going to have to set these weights in order to fit the data. Okay? Because I can't look at the target function and say, oh, that's the target function with this many positive regions and that many hyperplanes to decompose it and then go and write down the multi-layer perceptron. We can't see the target function. We only get the data, so we have to fit the data. And remember, when it came to fitting the simple old perceptron, it was already a very hard combinatorial problem. Okay? And we have PLA and pocket and regression for classification, and you can even use logistic regression for classification and so on and so forth. Okay? It's already a hard combinatorial problem with just one layer perceptron. So you can imagine how hard it is to fit the data with all these multi-layer perceptrons and all these weights with their interdependencies and so on and so forth. Cascading interdependencies. Okay. This is a very hard combinatorial problem to fit to the data. Okay. And that's going to sort of propel us to introduce instead of the multi-layer perceptron, the cascaded perceptrons, we're going to have to somehow soften this so that it's more manageable. The sign function is essentially what's causing all the problems. Okay? And what we're going to do is we're going to replace this sign function, which is non-differentiable, with the approximation of the sign function, a sigmoid, okay? Essentially tan h. And when we replace these sign functions with the tan h's, give ourselves multiple layers, multiple nodes per layer, the ability to set the weights, we get the multi-layer neural network. So let's erase. I'm going to show you the multi-layer neural network, set up some notation, okay? And we'll call it quits for today. Okay? So the notation is very important. So we'll set up the notation and allow time for that to sync because, think about it. We have to keep track of weights in every layer, different layers, and so on and so forth. So we're going to need a very systematic notation, okay? And this notation is, reasonably cumbersome because it has to sort of capture the whole, network. And so it's worth just sitting down and carefully writing down the notation, let that sync, okay, and absorb the notation, which we will use to talk about the nuts and bolts of the multi-layer neural network, or just the neural network. Okay, so let's erase, come back, talk about the multi-layer neural network. Speed, erase, bam, 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 bam. The multi-layer feed-forward neural network. In parentheses, multi-layer feed-forward neural network. I put those in parentheses because, they technically describe, the specific kind of neural network we're talking about. But typically we just say neural network. Okay. So, the input, that's fixed by the problem. Okay, so let's assume that we're in D dimension. So the input is this augmented input. Okay, so the input is 1, x1, x2, all the way to xd. Okay. Now it's cascaded perceptrons, that's the multi-layer perceptron. Okay. Except that, so in each layer, we can have something like a perceptron, except that it's no longer going to be the sign, it's going to be a sigmoid, okay, to make it softer, more manageable, basically differentiable, so that we can run gradient descent. Okay, so you have, let's say this is layer 1, okay, so, you have your vertices, your nodes, okay, then you can have layer 2, and you can have your nodes, okay, and then we can have layer 3, okay, and I'll just illustrate with just one extra layer here. Okay, so imagine that we're using 3 layers. So this last layer is called the output layer. So this is the output, h of x. Okay, and so what's going on? You're basically implementing perceptrons. So you can imagine that here I have one perceptron, put it in blue, okay, and here I have another perceptron, I'll put it in red. Okay, so remember there are weights, and you add up the inputs, you multiply each input by the weights, add up and feed it in here. And I'll put this, third guy perceptron here, green. Okay, so inside here we used to be the sign, but now we're going to put a sigmoid, so I'll call it theta. Okay, and then we have sigmoids in here. You can imagine that we can also have the sigmoid in here. Okay, and again, we are implementing perceptrons. Okay, so we have a perceptron here. We have another perceptron here. Well, it's like a perceptron because it's not quite a perceptron because that we're not taking the sign of the output. And a final perceptron here. Okay, and we have this third layer. Okay, we could keep on adding layers if we wanted to. Okay, and here if this is indeed the output layer, we just have one perceptron, one linear model, okay, but with the tan edge. Okay, so I'll put this in black because it's the final layer. Okay. And so there's just one output. So let us say that we have layers. So we have layers, and we'll use L to represent the layers. So you have layer 0, and the final layer is, we'll call it layer L. So here we have layer 0, layer 1, layer 2, layer 3, and in this case, big L equals 3. So that's the final layer. Now, if we wanted to refer to a node in this network, okay, if we wanted to refer to a node in this network, we will observe that the node can be specified by telling me what's its layer, okay, and in this layer, what position does it occupy? So a typical node will have, a representation as a layer, and we'll typically use superscript L for layers, okay, and its position within the layer, so I'll call this I. So this is, node I in layer L. Okay, and so if we want to refer to a quantity, but particular to a particular, that's let's say the input to this node, or for example the output to this output of this node, we could talk about the input, Li. That's the input to node I in layer L, or the output Li. That would be the output of a node in layer L at position I. Okay, and these guys here. So this is called the output layer. So this is called the output layer. And this is called here the input layer. Okay, no surprises there. And in between here are what are called hidden layers. Okay. And in this particular example, we have 2 hidden layers. Okay. Now, remember what I told you. We get to specify the weights on each of the edges. Okay. Now, what do I mean by... So multi-layer is kind of self-evident. We have multiple layers. What do we mean by feed forward? What we mean by feed forward is that, once you tell me the inputs, those feed forward to the next layer. And then those feed forward. The outputs of this layer feed into the next layer. And the outputs of this layer feed into the next layer. You don't have, outputs, going backwards. So the outputs of this layer do not feed into the inputs of this layer. That would become a recurrent neural network, much more complicated, okay, not within the scope of this course. Okay. Now in theory, you could still remain feed forward and have the output of this layer, feeding into the input of that layer. So you could have an edge going this way. We're not going to have those edges. It would still be feed forward. Okay. Basically, if you think of this as a graph, and if the edges had arrows, all the arrows would be pointing from left to right. Okay. And then we could immediately say that this graph has a topological sort. So as long as, the graph has a topological sort, you could think of it as feed forward, but, let's simplify. So this is layered, sometimes called leveled. So it's a leveled network, and it's feeding forward. So the inputs feed from the left to the right in the typical way we draw it. Okay, now let's drill down into a single node. Okay, so you have a typical node in your network. In your neural network, so let's call this node in layer L, and it's node I. Okay. And, it has some output. There's an output, and there's an input to this node. Okay. Now, what we will do is we will call this input the signal coming into this node. So this is the input. Okay, and we'll call this the signal SLI. So the signal that's coming into the node. And then there's an output. Okay. Output. And we will call this XLI. So the output of layer 0 is X0I, okay, which correspond to the features for your input example, let's say. Okay. And, the output is related to the input by this transform theta. So the most popular choice for this transform, or a popular choice. Nowadays there are, competing choices, but the one we will use is a standard sigmoid. So, theta of S, goes from, it's approximating the sign. So this is +1, this is -1, and so this is S, and so this is theta of S, the sigmoid. And a very popular choice is equal to tan H of S, the hyperbolic tangent. So tan H of S, this is the sigmoid, okay, that we will pretty much be focusing on. So you have an input to a node, and then its output, and these are related by X, L, I is equal to theta of S, L, I. Okay, so there's no rocket science here. Now, the interesting part in the neural network is, okay, how is the input constructed, and what is done with the output? Okay, you have an input and an output. Okay, so that's the output and the input. Now, what's happening to get the input? So let's take this guy, for example, this node. Okay, from the previous layer, or even this node, from the previous layer, you take all the vertices, all the nodes in the previous layer, and you're computing a perceptron. Okay, so there's a perceptron coming in here. Okay, so there are edges coming in. Okay, they all come in. Okay, and from the various nodes in the previous layer, and we add, okay, and that's what gives us the input. Okay, so you can think of a weight coming in from the previous layer to the current layer. So we will call this weight WL JI. So this is node I. So from the previous layer, node J, to the current layer, node I, WL JI. Okay. And in fact, what's going on is that these you could summarize the weights coming into this guy as just a perceptron. So we could call that little WL I if we wanted to. So there's a perceptron coming into this node here. Okay. Now what about going out? So let's look at what's going out here. Well, there's an edge, there's a weight going out to every node in the next layer except to the augmented one. Okay. So if you think about it, okay, so there's a node, there's an edge going out to every node in the next layer. Okay. And so since the weights coming into this, the edge weights coming into this node were WL, so these weights are WL plus 1, okay, and they're going from I, let's say, to K, from I to K. So the weights going into layer L plus 1 from node I to node K. Okay. Now, let's think about what's going on in this next layer. If we're focusing on, let's say, this node. So let's say we're focusing on this node. Okay, so what's going on in this layer is its weight comes in, there's another weight coming in, there's another weight coming, another weight coming. All these blue weights form a perceptron into this layer. Okay. Okay. Now, it's convenient to represent all these perceptrons that are coming into this layer as, a perceptron weights W1, perceptron weights W2, perceptron weights W3, and so on. So this matrix of weights, there are many weights in here, but it's composed of a set of perceptron weights W1, set of perceptron weights W2, set of perceptron weights W3, and so on, depending on how many vertices. So it's convenient to represent this set of weights WL as, the weights coming into vertex 1, node 1, so WL1, WL2, and so on. Okay, so this is WL. These are column vectors. Okay, but now how many are there going to be? Okay, so we're going to define the dimension of layer L. So the dimension of layer L is going to be DL. Okay, so you can think of this as node 0, the augmented 0, node 1, 2, 3, so node 1, node 2, node 3, and so on up to D1. Node 0, 1, 2, and so on up to D2. Okay, and then, the dimension of layer 0, the input layer is going to be D0, which is actually just the input dimension D. Okay, so how many perceptron weights are coming into layer L? WL1, WL2, up to WLDL. So that's the number of perceptron weights coming in to layer L. Okay. And each of these, so the perceptron weights that are coming into node I are WLI, which are part of this big matrix of weights. It's convenient to store all the weights coming into layer L as a matrix of weights. Okay. And then similarly, okay, we can store this as a matrix of weights. WL plus 1 is equal to WL plus 1, 1, okay, WL plus 1, 2, and so on, up to WL plus 1. Okay. So the weights going into layer WL plus 1 will have, there'll be dimension DL plus 1. Okay. So, just so that you have some practice with this notation, exercise. What are the dimensions of WL and the weight matrix WL plus 1? Okay. What are the dimensions of the weight matrix WL and the weight matrix WL plus 1? Exercise. Okay, now let's look at the inputs and the outputs of the nodes. So the inputs of the nodes, so there's an input to node 1, there's an input to node 2, there's an input to node 3, and so on. How many inputs are there? DL, if we're talking about layer L. So we can construct a vector. It's convenient to construct a vector, SL, the input vector. Okay, so the input vector SL, okay, which contains the input to node 1 in the layer, the input to node 2 in the layer, and so on, the input to node what? DL. Okay, so a vector of all the inputs. So here, so this here, the vector of all these inputs. So this vector coming in here would be the vector of inputs S into layer 1, S into layer 2. Okay? And the whole set of outputs, okay, X out of layer 1, X out of layer 2. So XL, okay, the vector of outputs from layer 1 is, okay, now we have the augmented one, and then XL1, and so on up to XLDL. Okay. So this is just some notation. Okay. So going into layer going into layer L is a matrix of weights, a vector of inputs, one for each node in the layer, okay, a vector of outputs, and then a matrix of weights connecting the layer L to layer L plus 1. Okay. Okay. So this is the neural network in terms of notation. Let me show you a slide, okay, with a nice clean summary of all this notation. Okay, and then we'll call it quits. Okay, so we can see here the nice neural network in all its glory. Okay, and let's drill down into a single node and all the details that we just discussed. Okay, there are the inputs to the layer, which is the vector SL, the outputs of the layer, which is the vector XL, okay, and the weights WL, the weight matrix WL connects layer L minus 1 to layer L, and the weight matrix WL plus 1 connects layer L to layer L plus 1. Okay, and so on the top right, you can see the neural network, again, in all of its glory, and drilling down a little bit of the detail of what's going on at a particular node. And let me end by showing you now what we started with, the biological inspiration, and then what we ended with, the neural network, the thing that, accomplishes the engineering success, that gets us the performance we want in predicting for out of sample. Okay, so on the right, biological inspiration, the neural network in your brain, okay? And on the left, the neural network that we use in order to engineer a model that predicts from input X to a prediction H of X, and hopefully we can get this thing to perform well out of sample. And we've seen in practice that it can work very well. So checking out for now. See you next time.